So previously we learned about this idea of electric potential. We talked about how it was related to potential energy, how to calculate it from that standpoint. And we also learned about how charges can create electric potential around them. Basically, whenever something creates an electric field, there is electric potential to go with that. So anything that creates an electric field creates electric potential. And we've sort of learned how to figure out what that potential is that's being created by a charge. But while that might sometimes be useful to know, it's very rarely our end goal. Simply knowing the potential at a point doesn't allow you to do much. The concept of potential becomes much more useful when we look at the potential difference between 2 points. So how potential might change as we move through a region. And so another way of saying potential difference is delta V, the change in potential. So that's what we're going to look at in this lesson. And again, I'll draw a bit of an analogy here with gravitational potential energy. If I have an object and I lift it to a certain height above the ground, well, that height has a potential associated with it. And when I place the object there, it will have potential energy. And I can maybe go ahead and calculate that potential energy, but simply knowing that potential energy isn't particularly useful to me. There's nothing that it really allows me to do or predict. But if I know the difference in potential energy between that point I've raised the object to and the ground, now I can do things like figure out how fast the object will be going if I drop it and let it hit the ground. And that's a little bit more useful. So to talk for beginners about potential difference, we're going to look at the definition of potential that we saw in a previous lesson. We said electric potential is the potential energy that a 1 Coulomb charge would have, or it's the potential energy per unit charge. Now we can take this definition of potential, this formula, and turn it into something that tells us about not just potential, but about potential difference. And the way we do that is by adding a delta to both sides. So if I know the change in potential between a couple of locations, then if I have a charge that moves through that change from one location to another, I suddenly know how much its potential energy will change by. And that is a very powerful thing, because that brings us to a point where we can start looking at the law of conservation of energy. If I know how much potential energy is changing by, I know there needs to be a change in kinetic energy or some work that needs to counteract that in order for energy to be conserved. And that lets me figure out all sorts of stuff about the speed of an object, about how much work is done on it. And suddenly this idea of potential becomes really useful because we're looking at how it changes. Now, going back to our analogy with gravity, I want to remind you of something, and that's that when work is done on a mass by a gravitational field, this changes its gravitational potential energy. So for example, that mass we were talking about earlier that we lifted up above our head, if I drop it, the gravitational field pulls down on it. the mass moves down, so there's a force and a distance downward, and then work is being done on it by the gravitational field. And as it falls, as that work is done, it will change its gravitational potential energy. So this is analogous to the scenario we have in electrostatics, where when work is done on a charge by an electric field, this changes its electric potential energy. So work done by gravitational fields and work done by electric fields both change potential energy. So both of these forces, gravitational force and the electrostatic force, are associated with a type of potential energy. And because of that, they don't count in our conservation of energy formula as work other. We have that work other term in that conservation of energy formula, and not all types of work count. Work done by gravity doesn't count. And now we know that work done by electric fields does not count. Just other types of work count here. Types of work that don't have a potential energy associated with them. Now, before we jump into an example, I want to recall a couple of ideas from the previous lesson that I think will be useful here. So, positive charges create high potential, and negative charges create low potential. In addition to that, positive charges are pushed away from high potential, and negative charges are pushed away from low potential. So positive charges that are creating potential will make that potential high around them, and positive charges that are being affected by a potential will feel pushed away from those high areas. And then the opposite with negatives. Let's do a bit of a diagram to sort of illustrate this. So normally in an area, if I have no charge, the potential will just be flat. The potential will be the same everywhere. But if I introduce a positive charge somewhere in that area, it will cause the potential around it to go high. Remember, positive charges create high potential. So whereas this potential was just a nice flat line before, when I introduce this positive charge, the potential around it suddenly gets really high. And if I add a negative charge, it will create a low potential. Now, before I finish drawing this, just let me move these charges down a bit so I have a little more room to work with. There we go. So again, this potential, when there were no charges around, was just a constant value. And around the positive charge that's creating this potential caused it to go high, and the negative charge caused it to go low. The drawings we did before were a little bit different in shape I think we drew this potential over here more like sort of a hill that went up and then down, and this more sort of like a valley that went down and then back up. In reality, I think I did that to make it look more like a landscape, to help sort of drive home this analogy that we can think of potential as like the height of some ground. In reality, though, the potential around a positive charge doesn't just go up a bit and then stop. It actually goes up to infinity, right, when you get to the center of that charge. And the potential around a negative charge will go down to negative infinity. So this is a slightly more accurate diagram than what we looked at before. So in blue, I've got my two charges that are creating this potential. The positive charge creating the high potential, and the negative charge creating the low potential. But remember, charges are not only used for creating electric fields and creating potential, they can also be affected by electric fields and potential. So let's use a different color here. I'm going to go with yellow to draw some charges being affected by this. So let's say I take a positive charge. I place it over here in yellow. Those blue charges will stay where they are. We'll pretend those are sort of fixed in place. And this yellow one is sort of free to move around. Well, positive charges are pushed away from high potential. So over here where this yellow charge is, the potential is kind of high, and the yellow charge is going to be pushed away from that to an area where the potential is lower, like over here. So that charge is going to feel a bit of a push to the right. Similarly, if I had a negative charge somewhere, like over here, we know that negative charges are pushed away from low potential. So we were talking in the previous lesson about how we can think of this positive charge as sort of like a ball that's trying to roll down this hill. We can think of a negative charge as sort of like a ball that does the opposite, a ball that wants to roll up hills. And if you place it there and let it go, it spontaneously rolls or moves to a higher potential. So that negative charge is going to want to move that way, towards an area where the potential is higher. Now this, we kind of knew this was going to happen anyways. If you ignore this whole black line and this graph of potential and just look at these blue and yellow charges, we would have said, well, yeah, this charge over here, it's really close to this positive charge, so it'll get repelled by that, and it'll get pulled towards this negative charge, so of course it's going to go to the right. And this negative charge over here, well, it's really close to this other negative charge, like charges repel, and it's going to get pulled by this positive charge because opposites attract. So yeah, of course, it's going to want to go to the right. So this idea of potential and positive charges creating high potential and other positive charges wanting to be pushed away from that high potential isn't totally a new idea. It still gives us the same results we knew long ago were going to happen. It's just another way of thinking about it that can be much more powerful. So let's just tidy up this this diagram here. This black line, again, as I've said, represents our potential energy. These yellow charges are the charges that are being affected by the electric field. So yellow is for the affected charges. And blue, I'm using for the charges that are creating the electric field of the potential. And so there are formulas that go with both of these as well. Again, we're just kind of reviewing these from last day. The formula for potential that refers to these affected charges is this one. So this Q down in this formula is for a charge that's affected by the potential. And the formula that goes with the blue charges, the ones that are creating the potential, is this one. So this Q in this formula is for a charge that's creating the potential. All right, so with all of that in mind, let's look at an example now. An electron accelerates from rest through a potential difference of 1.5 volts. How fast is it going? So I think before we start thinking about this question, it's worth thinking about the gravitational analogy. I have a charge that's accelerated through a difference in potential. In the gravitational analogy, I would have a mass that's accelerated through a difference in gravitational potential or a difference in height. So this is like if you take an object and you lift it up and you drop it, it will accelerate. And it will accelerate downwards through an area where there is a difference in height, a change in height. So maybe if you lift that object up 2 meters, it'll accelerate and accelerate and accelerate through a region where there's a height difference between the top and the bottom, where it started and where it finished, of 2 meters. So that's how I think we should think about this. The electron is like the object that we're dropping, and the potential difference of 1.5 volts is like the difference in height that it falls through as it accelerates. Now, just like in the case of a falling object, we could use the law of conservation of energy to look at how its loss in potential energy gets converted to kinetic energy as it falls and speeds up. We can do the same thing here. So let's start with the law of conservation of energy. Now, when I drop an object, there's work done on it by gravity. But remember, that work doesn't count here because when work's done by gravity, gravitational potential energy is changing. So that's already accounted for in those two terms. The same goes here. Because the force that's doing work on this object comes from this potential difference, this electric field, well, we have a potential energy formula for that. So it's counted here and here and not here. This is basically like in our diagram up here, if I took one of these charges, one of these yellow charges, and placed them there and then released them and let them go, they would be accelerated through a potential difference. The potential up here is one value, and then this charge might move to the right and go over here to where the potential is a different value. And it would be accelerated because of that potential difference. I don't need to push on it or use any other force to get it to go from left to right. It would do that on its own because of this electric potential, because of this electric field. And any work that's done by an electric field does not count there. So, in this example, work other will be 0. Now, what I'm going to do here, because I think it'll make this formula a little more useful for us in this situation, is I'm going to put all the potential energy terms on the right-hand side and all the kinetic energy terms on the left. So now you see on the right here, we have final potential energy minus initial potential energy. Well, final minus initial of anything is just the change in that thing. So this is change in potential energy. And on the left side, we have initial minus final. That's backwards. So that's the opposite of the change. It's the negative of the change. So this is negative change in kinetic energy. So this formula isn't hugely insightful. It's not something we don't already know. It just says that when no outside work is done on an object, any change to its potential energy has to be balanced by a change in its kinetic energy. If I lose potential energy, I have to gain kinetic energy. If I lose kinetic energy, I have to gain potential energy. That's sort of the essence of the law of conservation of energy. But having it written in this form can be particularly useful. Now, I'm just going to swap the left and right sides. That's just sort of my own preference. For whatever reason, I like having the potential energy written on the left, but it really doesn't matter. So this part here, the change in potential energy, well, remember we were talking about potential difference and how we can take this formula and convert it into this by adding a delta to both sides. And then we see that the change in potential energy is actually the change in potential, the potential difference, times Q. So we can put that in down here. Change in potential energy is the potential difference times Q. And the reason that is useful, that substitution, is because the potential difference is exactly the number that we are given in the problem right up here. So now we've got this formula in a form where we can take the potential difference we know and plug it in. Now, one thing that can sometimes be a bit tricky when we're talking about potential difference, we're often given these numbers, potential difference of 1.5 volts. But it's not really clear whether the potential is increasing or whether it's decreasing. It could be going up 1.5 volts as the electron moves. It could be going down 1.5 volts as the electron moves. All we know is there's a difference between the beginning and the end of 1.5 volts. But let's see if we can figure out which case it is. We know that electrons are negative. So if an electron is being accelerated, well, electrons, negative charges, are pushed from low potential. So they're going to go from a low potential to a higher potential. So if this electron is moving through a potential, it's going to go to a higher potential than it used to be at, right? Just like this negative charge here was moving to the left, where from an area where the potential was low to an area where the potential was higher. So in this particular case, although it doesn't tell us in the problem that the potential is going up by 1.5 volts, we know it is. Because it's electrons always go from low potential to high potential. At least that's the way they're always pushed. So that means our delta V is going to be positive 1.5. And the charge on an electron is negative 1.6 times 10 to the negative 19. So we can see we have negatives on both sides of the equation here. I can basically cancel those out. And this will tell me that the change in kinetic energy of the electron is 2.4 times 10 to the negative 19 joules. So as this electron moves through this electric field, again, I like to think of the electron as falling, only because it's negative. Instead of falling down, it sort of falls up. It falls to an area of higher potential. As it falls, it's going to gain kinetic energy, and it's going to gain this much kinetic energy. So how can I use that to figure out how fast it's going? Well, I know that change... Let's switch to a different color here. Change in kinetic energy is kinetic energy final minus kinetic energy initial. I'm just basically sort of undoing what I kind of did over here. Because this electron was accelerating from rest, I can say that the kinetic energy initial is 0. So the delta KE is equal to the kinetic energy final, or 1/2 m times its speed at the end squared. So if I take the change in kinetic energy of the electron, put that in here, the mass of an electron, put that in here, I should be able to find the speed of that electron and get it out there. And so punching all these numbers in gives me V equals 7.26 times 10 to the 5 meters per second. So, sort of the key ideas with this lesson are that this formula we have here, the definition of potential, actually can be used to tell us about the change in potential, or potential difference. And then the law of conservation of energy can often be rearranged, depending on the scenario, to give us change in potential energy as one of its terms, allowing us to combine that equation with the one up here, getting us to a point where we can use what we know about the potential difference an object might be moving through to find some stuff out about the types of energy that it's, or the amounts of energy that it's gaining or losing. Other than that, the one other thing that I really want to kind of highlight in this lesson is that positive charges create high potential, and other positive charges will then be pushed away from this high potential. So positive charges make high potential and they run from high potential. Negative charges do the opposite. They create low potential and they run from or are pushed away from low potential.